let me show you what this quiz was about. It was very, very simple. All you had to do was implement this equation, okay? So the answer for that, you have to type in and whatever, but let me show you the answer first, okay? Solution was this. That was the answer, okay? Nothing else. Just this was the answer. I know many of you did a load, word, and store, whatever, right?
Yeah.
That's fine for your testing, but here you see the register values and the memory values here. These are provided here so that you can test your code, okay? So the thing was, when we go all the way up to the top, your thing was mapping of the register value to whatever is here, and then implement the following, okay? That means you never have to use load and store. You just have to use a T0, 1, 2, 3, 4, and whatever other auxiliary registers to implement the equation. And how do you test it? This is what you do it. Whatever you want to write it, just like, okay, I want to test what if T0 was equal to like 2, and then T1 was equal to something, whatever. You put that in, run it, and see if you get the result stored in the whatever you're supposed to get it. What I mean is, you want to see a result that's in Z. Mapping for Z is T4, right? So if I set 1, 1, 1, 1, and run the simulation, register T4 should have 4, right? That's how you test it.
Yeah.
If you look at many of you who didn't get the score, the full score, was not because you didn't know how to write these 3 lines of code. I think you put a bunch of junk there, okay? That's why, as I said, like the first quiz, I kind of want to go easy, and that's why everybody got a full score. But please take a look at it during the break, how the grading was done. I think you should be able to see it, right? Your code and the test cases you missed, right? Because I think it used the test case I put it in was just that, right?
Yeah.
I tested with these 3 cases, and all was that plus that plus that plus that, whatever, right? Well, I don't know what the equation was. It was a plus plus minus or something? Yeah, plus minus. So if you do some magic, you're supposed to get this, right? That's how you test your code, okay?
Okay.
Please make sure to do. I'm not going to give you full score on today's quiz. The reason is you already practiced it, and the second reason is it's actually very hard, okay? Today's quiz is not as easy as 3 lines of code, okay? And I don't expect anybody to leave in the first 10, 15 minutes, okay? And I expect you to have a piece of paper. Because, it's fun, but it's not easy, okay? So, having said that, hold on. Let me go back because I don't want to reveal the quiz. Okay, there you go. All right, that's what the quiz was. What else? What else am I going to talk about? Oh, let's see when our midterm is coming. It's coming sometime, I think. Courses, 5565, fall, and then syllabus. Okay, so today is October 2nd. So October 9th is the fall recess. Okay, I don't know what that is, whatever, everybody just rest, okay?
Okay.
And then we have October 16th, which is. Okay, so let me go with this here. Where's the calendar? All right, so next week, no class. I didn't know that actually, okay? So that's good. 16th is going to be the last contents. And then 23rd is going to be the midterm, okay?
Okay.
So, here's what I'm going to tell you. By now, you've seen 2 versions of assessment, right? One was a multiple choice that you did it, or not multiple choice, but the easy ones, right? You just log in and then type do a binary conversion, write the number. That was one type, right? Second type was the one that you did last week, which is exactly coding, right? You're gonna have both of them on your midterm, okay?
Okay.
And I have multiple choice, but I haven't done the coding yet because I'm actually waiting to see your score from today's results, okay?
Okay.
Today kind of tests your IQ, let's put it that way, okay? Until today, let's say it was more about effort based, okay? You put a lot of hours, you got 100%, all right? But today is going to be actually challenging, all right? Although don't get the course because, you know, life, right? So, okay, that's good. I'm going to put the announcement on no class and what to expect on the following week. And also, depending on how you perform today, one class before the midterm, I might switch the contents, okay? Not switch, but maybe just the pace a little bit, okay? Depends on how we do it. This is the reason why I dedicate a lot of weeks for coding. Okay, that's cool. Now, we're good to go, so we're going to start on the set less than instruction. Set less than instruction, what is this? Well, let's go back and check out our chapter 3 and then go to the instruction summary. Set less than SLT, right there. So what it does is that compare the values, okay? Register A, write 1 to register A, that's your destination, all right? If B is less than C, okay? So remember the order, B is less than C, then you're going to set A to 1, otherwise write to 0, okay? So that's the logistics of the set less than. So right there, we have this instruction here, set less than T2, T0, T1. So 5 is less than 10, right? So we're going to set T2 to equal to 1, right?
Yeah.
And then after that, branch not equal. So T2, is that equal to 0? No, right?
No.
So we don't take a branch, we just continue on. Okay? So let's see what it does in the animation. So we're going to start the animation here. Okay. That instruction we execute. And then T2 is set to 1. And then after that, we go in and do this. Okay, so we don't take a branch. We just go on, okay? Alright, I'm not going to do all of this. We'll look at it. Branch on less than instruction. Branches is the first, register is less than the second. Branch on less than equal, okay, BLE. Okay, only thing difference is less than or less than equal. This was greater than, last was greater than equal to, okay? There's a temporary register that's reserved. That's the register at, okay? So that's used by assembler to hold the temporary value needed to include pseudo instructions, okay? Which means you never touch it. That's all I'm saying. So what does that mean? Okay. You're going to understand a little later. We're going to come back to this when we talk about the processor. You never write native instructions, okay? Because I told you, you should never touch AT, okay? So you only write BLT, BLE, BGT, BGE. That's it. But on the actual machine, this becomes 2 instructions like that. That's all they're saying, okay? Mm-hmm. Again, at this point, don't worry about it. Just understand these are, that's what we call it pseudo instructions, right? Yeah, pseudo instructions, okay? These are pseudo instructions, not actual machine instructions. But it makes our life easier, so that's why. As I said, AT, in anywhere in your code, you know, you should never see AT. Okay, but just understand it exists. All right. So, obviously, this is another easy thing. All right, implement bit to branch when T3 is less than T4. So we are testing this. Let's take a look at it. T3 less than T4. We're going to set T5 to whatever, okay? T5, okay? And then, if this is less than 4, T5 is equal to, okay, you know what? Never mind. I can only touch the first instruction, so let me take a look. The temporary register is not equal to 0. If this is not equal, jump. So let's see, AT should be the destination. Okay, set less than. If it's not equal, okay. Jump. If this is true, jump. If this is true, then you get 1. That's not equal, then you go jump it. So that logic makes sense. Okay, I got it. All right, how about this? You have to look at the logic a little bit. That's why BLE to branch. So implement BLE. Okay, you branch to L1 when 3 is whatever, right?
Yeah.
So this is set less than equal. Oh, we don't have that option, right? What can we do?
Change the position of T3 and T4. Yeah.
So this is less than 3. That means it's opposite of this, right?
Yeah.
Then we're gonna set T5 maybe, okay? Or AT.
Okay.
Or no, T5. Hold on. Wait, one second. So I should not mess up with T5 because T5 is using the teacher instruction, so I don't want to mess up with it. So I have a 3, 4. Maybe I use that. Does it make sense? Let's see. So if the condition is false, this is set 1, right?
Mm-hmm.
So if it's 1, that means 1 is now, if it's false, and that's not equal to 0, that means the condition is false, then branch 2. That's what I think is correct. Yeah. Okay. Branch if branch to L1, so whatever, I think it should be a branch instruction. Which one am I going to use? I don't know. Let's see. Less than, do I have less than? Yeah, so if it's T0 is less than T1, branch less than that. Branch if T0 is less than T1, jump to L1. That's correct. Okay?
Okay.
So that's where set less than is used. Okay, before we go into input and output, let's do one more exercise. Okay, write an instruction. If T1 is less than T2 and if T2 is greater than T3, branch to L1. Okay? So what I'm saying is, you write this piece of code here, okay? And then L1 is somewhere down here, okay? And then there's some code which you don't care. These, okay? You don't care about this code, okay? I want you to write this piece of code, which is exactly this, okay?
Okay.
Go ahead and try it.
By the way, there are multiple ways to do this. Actually, there's no one solution. Okay.
By the way, you guys can talk to each other, okay? It's not a quiz or exam, so.
这样就只用一个 J。但好像不是，这样有个问题，因为它这一个是一行一行，读下来嘛。如果你这一行，
那如果这个是否的话，那就直接 after。
对，它就不会读下一行的，所以它要反过来才能一行一行读下去。
但是如果这要是肯定的话，它就会直接跳到 L2了。后来如果这个肯定再跳到 L2，它就直接把这样这个跳过了。
对，就这一个是刚好符合第一个情况，然后你就跳这个。
如果要不是的话呢，就会走到 J after。
对。
然后 J after 就 after 这儿了嘛，就好。
那好像也可以，他没有要求其他的。 他只是说符合两个条件。
避免了你就能用这个 after。
对我这个是。
如果要是这个是否的话，
就如果他是否的话，他就直接 L2 直接跳出去了，就相当于跟你的。
对呀，你否的话你还没检测2和3的。
因为我这个是相反的嘛，如果它相反的话，
会走到下一行在这儿了。
对，如果相反就说明符合第一个 T1 小于 T2，然后就验证下一个。如果是用的就 L1，然后就追点。
是 less 的 less。
对 L1的。
然后
就这个就是。
要是否的话，然后你就能用那个这个 after。
对，就少了一个那个，我觉得应该都可以吧，他就没要求。我之前那个练习有一道题目是差不多这个，他要求多一些，所以就他刚好是反过来写的。
逆向思维。
Okay, I'm going to show you the answer. Okay, so this is the answer, okay? For me.
SGT 是怎么来的？还有 SGT 了。
这个是个想法，确实是。
它就两个，如果都一样就2样。我不知道还有那个 SGT， 它不是只接到了 SLT 吗
？SLT 对，还是这个。
有这个东西的。
下面是另一个 SGT。
标上也没有。
但是你不乱去碰到这样的数据。
Okay, let's do one more practice. Okay. This is the next solution practice.
那照抄那一个不就好了？它好像这个比较简单直接。
它这个就是正经的一行一行一行。
它这个就严格一样一样做下去。
Let me just take a look at another one. Next is, the next one is a set less than input output. Okay, so you can read about this later, but I'll explain what happens. So this is how computer input and outputs work, actually. So whatever gets displayed on your monitor and how you type in the keyboard, it is all communicated through memory, okay? When you type the letter on the keyboard, it never directly goes to the CPU. It always has to go through the memory. Same thing for the output for a monitor. So what happens is you do computation, whatever number that you want to output to your monitor, right? It goes to a special region in your memory, okay? And then when you write there, the screen basically grabs it, okay? And that's why you see the frequency, right? You hear 60 hertz, right? 80 hertz, right? That's how frequently they're pretty much looking at the memory. If you take operating system class, you'll know why that's the case. Unlike monitor that regularly check the memory, your keyboard is different. So I'm not typing anything right now, right? My CPU will never check the contents of this, okay? How it happens is, in operating system, it's called the interrupt driven, okay? So when I type something in the keyboard, it gets written onto the memory, right? But then how does the CPU know that I typed something? Is you have to set this into 1, okay? So when this special memory location is 1, then CPU knows that, okay, the user typed something, go grab that, whatever keyboard input that is, and then do whatever you want to do, okay? So it's better with the animation, to be honest. So let's go from the beginning. The first one is outputting. So you do that, you put 99, and that gets written into the output. You write that again, and that gets written into the output, okay? That's how it works. I think all of you know Python programming. There's something called the print, right? In C++, it's a printf, right? In Java, it's a system.out. This is the reason why you never see parallel print. You can parallelize add, you can parallelize load, and you can. Every language has a parallelization, right? Or what's called coalescing, okay? You don't have that for the IOs because it's still a very manual process like this. So, if in a scientific computing, I'm talking super high performance computers, what usually happens, okay, not that, okay, let me see. In operating system course, I think if you take a proper operating system course, you have to learn how to write multi-threaded programs, okay? That means the one process and multiple threads. They basically execute like this, right? And they're all done. So you know the difference between thread and process or not really? Process, you have your dedicated memory, okay? That's yours. Nobody can do anything about it, okay? And then thread, so you have multiple processes. That means you have multiple. This is process 1, this is process 2, 3, 4. They don't share each other, okay? Thread is different. I have one process with the multiple threads. They all share the thing together here, okay? So, again, to tell you a little bit of history of computing, this concept of a multi-process and multi-threading, not multi-threading, yeah, multi-threading, was exactly the reason why Google Chrome browser, conquered the market. Each tab on your Chrome browser is a process, okay? When you go back to 10 years ago with the Microsoft Windows Explorer, right? Windows Explorer, each tab was a thread, okay? So why is it better? Well, let's think you go back to 90s in Windows, right? When in 1990, whatever, 98, almost nobody had internet, right? And the internet was on the dial-up modem, right? The phone line, you know what I mean, right? If you're old enough, you know what I'm talking about because data traveled through the phone line, the dial-up modem. And at the time, they had something called ADSL, which they thought was super fast, right? All right. Your home, if you're, unless you're super, tight on money, I'm sure your internet is 100 megabits per second or above, okay? Like, I don't think anybody has 25 or 50 megabits per second these days. Back then, I told you megabits, right? Back then, we were talking about kilobits, okay? So we were talking like more than 1,000 times smaller amount of data. So what that means is the phone line cannot, why I tell you it's a dial-up system, because you have regular telephone, right? You just talk on the phone, all they had to transfer was voice, right? So that's why the phone line doesn't need that much data, right? You talk crazy, it doesn't matter. You're still going to carry the same amount of data, okay? Then we use that to transfer the internet data, right? That's why if you look at the very first internet, the website, if you really wonder, you can look up something called Netscape, okay? The web page looks extremely, extremely simple. Because you cannot load high definition stuff back then because we don't have that much bandwidth on the internet, right? Okay, that's the history of how internet started, right? And then they go to ADSL, and many of you, right now, you're choosing between TELUS and Shaw. Sorry, it's a Canadian thing, okay? It's more like Xfinity and Time Warner, okay? History about TELUS and Xfinity, TELUS and Shaw, TELUS and Rogers, okay? Let me go properly. Some of you have TELUS, some of you have Rogers for your internet at home, right?
Yeah.
It used to be a completely separate service. The internet from TELUS used the telephone line, and internet from Shaw used the cable. TELUS was a phone company, and then Shaw was a cable TV company. Okay, so now it's everything fiber, it doesn't matter. But back then, it mattered. And that's why Shaw was better in many aspects, because coaxial cable was used to transport the TV signal, right? Which was actually a better, pixel and all that, right? TELUS was the telephone company. They were still the phone line stuff, right? Then the TELUS improved. Eventually, they all got the same. But that's the history why almost every major North American city, you will I'm saying city, not rural area. If you're in a city, you will almost always have the two major internet providers, actually, for that reason. One started off with a phone line, one started off with the cable TV. And that's why even in the U.S., you always get two, no matter what, unless you're a rural area where you only have one option. That time, that's why if you look at it, the internet. I went too far back. But that's the reason why the website did not have a lot of contents, okay? So Internet Explorer, if you look at it, started in 90s. Well, you use Microsoft Edge, okay now. So I'm talking Internet Explorer, that's gone, IE, right? Well, for them, multi-threading was not there in the beginning. Very first processor that had the multi-threading capability was probably in 2002, what's called the Pentium 4, okay? Before that, there was no concept of multi-threading because no one can support it. So internet got invented in about, internet got really popular in late 90s, right? I'm sure you heard of a dot-com boom, right? So back then, think about it, internet and a single thread only, single thread, single process. That means, who cares? I just write the single process Internet Explorer. And multi-process stuff didn't even exist, right? So they made Internet Explorer. And then, let me just give you one more example. Before Windows 95, you have Internet Explorer, and you want to actually open Microsoft Word, you have to actually close the Internet Explorer and open it. Because they had no concept of multi-process. Only one process survives on your computer. You can do one job, shut it, open another one. Windows 95 and or 98 introduced the concept of multi-process. So now you can have two windows, finally. But still no concept of all that, right? So if you're a Microsoft, and at the time you had to come up with Internet Explorer, well, you just obviously it's a single process thing, right? But then Pentium 4 was a big breakthrough. Finally, we can do a parallel processing. And Microsoft back then was, okay, you know what? People start having many web pages now, right? So what's the obvious logical choice? Is the multi-threading. They went to multi-threading and they got super fast. And Netscape is gone basically by then, okay? That was not a competitor. So they're doing okay, and I think you realize why people switched over to Chrome. Because in the very early days of Chrome, Internet Explorer was so slow, and Chrome was what's called a lightweight. Because if you open Google, you know, you have nothing. Not like Yahoo, right? Yahoo, you had the stock, news, and weather and all that. That's all gone. Google was clean page, a search page, and the loading was way faster. And they did something different. They made a tab to be a process rather than multi-threading. And that made multi-tab internet browsing way faster. Back then with Internet Explorer, if you switch the tab, which is Control Tab, I think, or Alt, it's a Control Tab, I think, Alt Tab was only one of them. The switching speed was very slow actually, because what happens was the threads were sharing the memory, and that they have to go in, and that has to exit until the next thread comes in. But in case of the Chrome, it doesn't matter because, okay, I'm switching it, who cares? I have this memory right there, right? So that's why Chrome actually started gaining the popularity, actually. And eventually, Microsoft realized, okay, you know what? Internet Explorer from 90s cannot compete with Chrome. That's why you have Edge, actually. So that's the difference between the process and threads. And that was a very classical example of the competition between multi-threading and multi-process. And eventually, multi-process won. And guess what happens right now? Chrome start putting a bunch of junk now that what used to be a tiny process like that, simple design, right? Well, if you look at your activity monitor on your Mac, you can see that Chrome is the largest one that takes your memory at this point, right? History repeats, okay? And what's more efficient right now? It's all about the fighting on the memory, by the way, okay? So which browser is quite efficient? I don't know the event, absolute metric, okay? But Safari is actually very efficient in terms of memory management right now. Well, I don't use it, but. So again, it's all years of just how computing has evolved. So having said that, what happens? Why I talk about threads? If this is 99 is written by thread 1, 408 is written by thread 2, what's going to happen is, if you don't do proper programming, the orders can be switched. And you will see that in any multi-threaded programming, printf or print statement, you must make sure the order, otherwise random stuff gets printed. I'll be honest. In any other, if you ever do C++ programming, if you do multi-threaded, it's completely possible you're gonna get 99408 or 40899, or you can even get 40989. Okay. That's why I/O is one of the few things where you cannot parallelize. Okay. No matter how you improve the system, this is how it's been written since 80s and 70s. You can't parallelize because this is exactly how input and output works with the memory. Okay. Doesn't matter how fancy monitor you buy, there's only one slot in memory where you can use it for the output purpose. So that's how it works, okay? So output goes in, and there you go. However, input is a different story, right? I only talk about the output. Input here is, you can read it here, input, special hardware, put this, and then write one to it, still running the processor, hey, the input's ready, go grab that character. And what's going to happen? It goes, grab the character, and do whatever you need to do, okay? That's how I/O works in a computer. CPU side, nothing fancy. You still write the assembly code, okay? Only thing you have to know is there are special memory regions that are used for I/O, okay? And that's why I think you heard the name I/O map memory, right? That's that region, by the way. Here is an input and output code. I'm not going to go over this, because there's nothing special about this code than what you did last week. Same load and store, do whatever you need to do, and then just store back into it. It's same load and store, just that you have to have a special region in memory, that's all, okay? Alright, that's all for me. Why don't we take a break till 4:25, okay?